Hello students, welcome once again to our YouTube channel. Before I start today, I will request you all, if these videos are helpful, the content is helpful, so please do subscribe the channel, and of course do like the video also. That will help us. Okay, so now moving to the next chapter today, we are going to take up the questions of permutation and combination. I believe you would have, at least few of you would have tried to solve those questions. Okay, so let's start, and then again of course the result will be out anytime soon. So best of luck to all of you for the upcoming result, and then we have to increase the pace of preparation for the upcoming JEE advanced paper bachcho. So chaliye, let's pick up the first question. The number of distinct throws when 10 identical dice are thrown is. So we know a dice has 6 possible number as a possible outcome. Okay, so there are 10 identical dice, and every dice can show you any number between from 1 to 6. So what are the possible outcomes? Okay, now see, for me I will say that I have 1 2 3 4 5 6. We have these things as the boxes. Okay, and I have, like, let's say okay, so 1 2 3 4 5 6. So these are 6 distinct numbers. So I'm seeing this question from the in the opposite side, or in the reverse direction. So it's the like 1 2 3 4 5 6. I'm seeing them as 6 distinct boxes and 10 identical dice. I'm looking at them as 10 identical dice, as 10 identical objects. Okay, so 10 identical objects with 6 distinct boxes. In how many ways we can put these 10 identical objects in 6 distinct boxes? Isn't that? See, what's going to happen? It may happen that 1 appear 2 times, 2 appear 0 times, 3 appear 5 times, 4 appear, let's say, 1 times, 5 appear 1 time, 6 appear remaining number of times. Remaining number of times means the total sum has to be 10 here. Isn't that? So again, what I did, I just took the numbers as the boxes, and I am allocating the dices, the objects, to those boxes. Okay, so if I say we get x1 number of balls here or objects here, x2 here, x3 here, x4 here, x5 here, and x6 here. Now what does that mean? That simply means, like, if x1 is 2, so 2 dice will show 1. Okay, x2 is 0, so no dice shows 2. That's it. So now sum of all these numbers, x1 plus x2 plus x3, x4, x5 and xs, how much should that be? That should be 10, because we have 10 identical dice, or as I am saying, 10 identical objects. Okay, now which type of solution are we looking for? We are looking here the number of non-negative integral solutions. So non-negative integral solutions. So how many non-negative integral solutions we have? So for that, I'm giving you the direct result here, though we can easily derive it, but I won't go for its derivation. So we have r variables, and the sum has to be equal to n. The number of non-negative integral solutions are n plus r minus 1, c r minus 1. Okay, so that what you have to use directly. So the number of non-negative integral solutions are 10 plus 6 is 16, minus 1 is 15. 15 c5 should be the answer here. Okay, so the answer should be 15 c5 bachcho, and that's it. Okay, so yeah, okay, fine. So that should be the answer, right? And see, non-negative integral solution. See, why did we go for non-negative integral solution? Because any one x1, x2, x3 could be 0 here also. So any one of them can be 0 also, bachcho. Okay, so that's it. So that's the answer for the first one. And then moving to the next one. Which of the following is our R2? There's a correction here. It should be in the question, I think it's a PDF, this should be 6 factorial here, and in the PDF itself, if I am not wrong, it should be 5 factorial there. Okay, so 62 into 5 factorial. Let's see. So now see, look at these statements. So if we can relate these statements to one or the other form which we already know, so which are those forms? See, looking at both the first two statements, rather all four statements, they should remind us about the principle of inclusion and exclusion. The principle of inclusion and exclusion. So what it says if we have R distinct boxes and n distinct balls, in how many ways we can put these balls in R boxes such that no box is empty. So in how many ways you can put n distinct balls in R distinct boxes such that no box is empty. Okay, so what's the way? So the way of to get the answer is, the one direct way of getting answer, at least getting expression is, so that the one way of getting the expression is using the principle of inclusion exclusion. What does that mean? That means first we count all possible ways of distributing balls in the boxes. So for first object we have R choice, for second object we have again R choice, since there is no restriction for all possible cases. So for every object we have R choice, so for n objects we have R raised to the power n choices. Now from them, all possible ways, remove those ways when at least one box is empty. So which box? We will say, okay, out of R, select one box, RC1 ways. Now you are left with R minus 1 boxes, okay, and then count all possible ways in which you can put n objects in R minus 1 balls. Okay, now see, when we counted at least one box is empty, so in that include at least 2 boxes, at least 3 boxes, or exactly 3 boxes are empty, include everything. But then there will always be a repetition, bachon. Okay, so for that, now we will add the cases when at least 2 boxes are empty, and that continues, and then subtract at least 2 boxes, 3 boxes empty case, and that continues, so on till you reach to the case when all the boxes are empty, RCR, and then you have 0 possible case, because when all the boxes are empty, RCR, there is no box in which you can put a ball, so every ball has no choice, 0 choice, so you end at 0. Okay, so that's your principle of inclusion and exclusion. The point here is, and how can you relate this expression with this one, and that is, see, the power doesn't change because that is number of balls, whereas the base is changing by 1 with every term. Okay, why? Because that represents the number of boxes. Okay, so now let's come back to it. So 5 raised to the power 6, 4 raised to the power 6, 3 raised to the power 6, the power will give us balls. So for the first one we'll say we have 6 distinct balls and 5, that's it, that's the largest possible number, 5 distinct boxes. In how many ways you can put balls in the boxes so that no box is empty, and you get this expression. So the left hand side gives us the expression which stands for no box is empty when you have to put 6 balls in 5 boxes. How many ways are there? Okay, so that's the ways, but then how can you get the answer? So is it equal to this one or not? So for that we have another way of getting this expression or solving this question, and that is, see, we have 5 boxes, 1, 2, 3, 4, 5. We have 5 boxes here. Okay, we have to distribute 6 balls in it, and then see what are the and no box is empty. So in how many ways the distribution rather I will say grouping is possible. So I have to group 6 distinct balls in 5 groups such that no, I mean, of course there's at least 1 ball in every group. So the only possible way of counting it is, that's it. 4 groups will have only 1 ball each, and 1 group will have 2 balls. In how many ways you can form such a group? The formula for grouping is all possible objects, or total number of objects factorial upon divided by the factorial of each number in every group. So 2 factorial, 1 factorial, 1 factorial, 1 factorial, 1 factorial, which is always 1, and divided by 4 factorial. So why this 4 factorial? Because there are 4 identical size groups. Remember, till the objects are distinct, the groups can't be identical. So that's why if you would have marked my statement, I said identical size group. So the size of 4 groups are identical, you divide by 4 factorial. So that's the number of ways of forming such 5 groups. Okay, now once you have 5 groups, what does that mean? You have 5 bags ready with you. You have 5 bags. Now you have 5 boxes. In how many ways you can put 5 bags in 5 boxes? 5 factorial ways. So that's distribution. It's a 2-step process. So it's 6C2 into 5 factorial. So that is the correct one. Clear? Now moving to the next one. Now mark here. The power is 5, which is same throughout. So there are 5 distinct balls. And the largest number in the expression, not possible, largest number in the expression at the base is 6. So 6 distinct boxes. And now again the same expression. Okay, so what the statement should be, and how many ways you can put 5 distinct balls in 6 distinct boxes so that no box is empty. Now you tell me, is it possible? Because you have more boxes than number of balls. So one box at least has to be empty, so the answer is 0. So that's also correct. Okay, so that's really a good way of solving such a series. I mean, if you try to solve this series in any other way, I think it's going to be extremely difficult. Okay. So if you can relate it with inclusion-exclusion principle, no box empty case, we can see the answer directly, at least in the second case. Now moving to the third case, of course it's the same one as the 6 balls in 6 boxes. 6 balls and 6 boxes, so it has to be 6 factorial, no box is empty, so this is 6 factorial, so that should be also be the answer. So answer should be A, B and C. Now moving to the last case, last B and D are exactly same. So B is correct, D can't be correct, so that's not the answer. So the answer in this question, the second question, should be A, B and C. I believe all of you would have understood the way we can apply the inclusion-exclusion principle, and when do we apply? We look at it as the best standard example to understand it is the distribution of balls in the boxes such that no box is empty. Okay, so that was a really important question, that's why I selected it for you people. Now moving to the next one. There are m seats in a row, out of which n are to be occupied by n persons, given m is an even number and m is greater than 2n. The number of seating arrangements such that each person has exactly one neighbor. What does that mean? That means n is an even number. Okay, let's say you have 12 persons. You will make them sit in a group of 2 each. 2 persons together. Okay, and then there's exactly one neighbor. What does that mean? 2 persons sit together, and then there has to be a gap of at least 1 seat, 1 chair. Okay, so at least 1 chair has to leave vacant between any 2 groups, and each group will have 2 persons. Okay, so the number of given m is an even number, the number of seating arrangements such that, fine. Now see, if I mark m seats, let's say these are m slots, m seats. Okay, now I have to make it how many groups? I have to make it n by 2 groups. Okay, so we have n by 2 groups. Each group has 2 persons. N by 2 groups, each group with 2 persons. So when you make them sit, of course, a group will occupy 2 places because each group has 2 persons. Okay, so in totality we know we have to make it n persons. Okay, now if you have to distribute these n by 2 groups, so let's say I selected this as one set of pair of chairs for the first group. So before that, I will say I am left with x1 number of chairs. So similarly, if I select this one, so I have x2 number of chairs between the first and the second group. Likewise, if I select this one, x3 number of chairs. And how many such things are possible? Of course, I will have one variable for the chairs left at the last. It may happen that the last group occupy the last 2 chairs, but it may also happen that there are 1 or 2 chairs left, or maybe any number of chairs left vacant at the last also. So how many variables we need? So again, as an example, if we have 12 persons and we divide them into 6 groups, 2 each. Okay, so then you have 7 variables. Why? Because see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, maybe like this. So if I put 6, 1 here, maybe 2 here, 3 here, 4 here, 5 here, 6 here. So before 1, we need 1 variable to define the number of chairs left vacant. Between y2, 3, 4, 5, 6 and 7. So you always need plus 1 variable in such cases. Okay, so how many variables I need? I need x n by 2 plus 1 variable. I think all of you would have understood. Okay, now if I add them up, so the x1 plus x2 plus dot 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 x of n by 2 plus 1, how much should that be? Of course there are n persons, so they will occupy n chairs, so m minus n chairs are to be left vacant. Okay, that's it. Now out of this n by 2 plus 1 variable, 2 variables x1 and x last one by 2 plus 1 can start with 0. Why? Because it may happen that the first group is occupy the first chair and the last group occupy the last chair. So you may not have even a single chair left vacant at the corner. So it is possible, but between any two groups there has to be at least 1 chair left vacant. So xi should be greater than equal to 1 for all i starting from 2 till n by 2. Okay, so now that means x1, x2, x3, x4 till xn2, they all start with 1. So for that I will introduce new variable and I will say, okay, y1 plus y2 plus y3 and so on, yn2 by 2 plus yn by 2 plus 1 should be equal to m minus n minus n by 2 minus 1. Why? See, what am I going to do is, I will say let x2 be 1 plus y2. So in that case, since x2 start with 1, y2 will start with 0. Similarly, x3 is 1 plus y3. So y3 start with 0. Likewise, as I said, the second last variable 1 plus yn by 2, and here also y. So now all can start from y1, and y1 is same as x1, and this is same as xn by 2 plus 1. So all the variables here from 1 till n by 2 plus 1, they all start with 0. So now I'll be, okay, so how many times 1 you have in LHS? So you had n by 2 minus 1. By out of n by 2 plus 1, you leave 2. You are left with n by 2 minus 1. So 1 by 2 minus 1, I took it that side, and this is nothing but m minus 3n by 2 plus 1. All of you agree, okay? Now, what are we looking at? We are looking at the number of, again, the same non-negative integral solutions. So the number of solutions are, number of variable is this, the n is that. So sum m minus 3n by 2 plus 1 minus, plus rather, number of variable n by 2 plus 1 minus 1 c n by 2 plus 1 minus 1. This is gone, this is gone. So it is m minus n plus 1 c plus 1 c n by 2. That's the number of ways of selecting the chairs. Now once you select the chairs, there are n chairs which you have selected for n persons. In how many ways they can occupy the chair is n factorial, and that should be the answer. Okay, so that should be the answer here. So C part is the answer. Okay, so that's the use of multinomial. Okay, in this question and in the previous one also we use this, but in previous one we use actually the inclusion exclusion principle. Now moving to the next question. Now see, that's an interesting question where several of the students committed a mistake because they didn't read this statement properly. They are digits. So A1, A2, A3, A4, A5 are the digits. Being digit means they can be any number between 0 and 9 only. 0 and 9 only. Okay. Now how did I approach? I said, okay, 2 raised power A1 plus 3, I will write it as 4 minus 1 raised to power A2. 5 as 4 plus 1 raised to the power A3. 7 as 8 minus 1 raised to power A4. 9 as 8 plus 1 raised to the power A5. Now what? They have to, the number, we have to find the all possible 5 numbers A1, A2, A3, A4, A5 so that this expression is divisible by 4. Now see, whether A3 is even or odd, A5 is even or odd, here when you expand it, you will get the number which is a multiple of 4 plus 1. Here when you expand it using binomial, you will get a number which is multiple of 8 plus 1. In any case, multiple of 8 means multiple of 4. So here also you will get some multiple of 4 plus 1 for every A5, whether even or odd. Here also you will get a multiple of 4 plus 1 for every A3, even or odd. So that means for A3 and A5 we have 10 choices. So whether from 0 to 9 you put any value, you are going to get 4m plus 1. Even if you put 0, A3 0, you get 1, which is again in the form of multiple of 4, 4 into 0 plus 1. Okay, so if I start counting the choices for A3 10, for every A3 you have 10 choices, for A5 2. Now, if A2 and A4 are both odd, if A2 and A4 are both odd, you will get minus 1 at the last here, minus 1 at the last here, which will cancel plus 1 here and plus 1 here. Okay, so if A3 and A4 are odd, you will get 4 and minus 1 here, 4L minus 1 when A2 and A4 are odd. So 1 minus 1 get cancelled, the entire term is divisible by 4, isn't that? So that means, and now how many choices you have for odd? So you have 5 choices, 1, 3, 5, 7, 9. Into 5 for every A2 you have 5 choices, for A4 also. Now, since the number except this one is divisible by 4, so what are the choices for A1? So for A1 the choice starts from 2. You got 2 square is the first number which is divisible by 4, and after that 8, 16, they are all divisible by 4. So A1 can't be 0, A1 can't be 2. So you have 2 choices here, okay, rather 8 choices here. So that's the first case when A2, A4 are odd. Similarly, let's count when they are even. See, when A2, A4 are even, so in that case it will be 4n plus 1 and 4l plus 1 when A2, A4 are even. And in that case also 1 plus 1 plus 1 plus 1, that's 4. Again a multiple of 4. So again this entire expression is a multiple of 4. So again the same choice, 10 into 10 into 5 into 5 into 8. Exactly same thing, A2, A4 are even. Now the last choice is, what if this is even, this is odd, or vice versa. This is even, this is odd, or this is even, this is odd. Plus 1, minus 1, or plus 1, minus 1, they will get cancelled. We are left with 1 here, we are left with multiple of 4 plus 2. So when any one of them, so let's say A2 is even, A4 is odd. Okay, so in that case, of course, A3, A5 has same choice, 10 and 10. But 5 choice for even, 5 choice for odd, and into 2. Why into 2? Because they can reverse the situation, odd even odd. Okay. Now, the final number again, till here, just a minute, wait, where is it gone? Yeah, fine. Okay, so the final number till here is multiple of 4 plus 2, plus 2. So that means here now we don't have a choice. It should be 2 plus something, 2 plus 2. A1 has to be only 1. You take any other number that may not be this, that will not be divisible by 4. So A1 has to be 1 here. So that's the choice. So total choices are 10 into 10 into 5 into 5 common, 8 plus 8 plus 2, and you count it. So 18 into 25 into 100. That's it. So you do it. Solve this and you get K. You'll get K. Okay, I've already solved it for the doubt here in this campus students, for our campus students. So now moving to the next question. Now that's an interesting question. Okay, the question is n1 is x1, x2, x3, n2 is y1, two-digit number. How many pair of n1? So that n1 can be subtracted from n2. So y1, y2, y3, x1, x2, x3. So you can subtract n1 from n2 without borrowing a number. Without borrowing a number means every time the number which is above the other one has to be greater than or equal to the other one. Okay, so it has to be greater than equal to. Similarly, y2 is greater than equal to x2, y1 is greater than equal to x1, but y1 and x1 can't be 0. Why? Because both are 3-digit number. Without borrowing. Okay, now see, the point is that in how many ways we can select. See, it's a simple thing. These are 2 digits, 2 numbers. Okay, rather 2 digits, not number. They are 2 digits. Okay, there are 10 digits. So just select 2 out of 10. Just select 2 out of 10, bachon. Okay, and then So how many ways it is? 55. See, don't have a choice of arrangement. We don't have a choice of arrangement. Why? The larger one, let's say you selected 5 and 7. So this has to be 7, this has to be 5. So you don't have a choice of arrangement. So 55. But then they can be equal also, because nothing is said that the digits should be non-same. How many pairs of, so that n1 can be subtracted from n2 without borrowing. If they are equal, then also it's fine, isn't that? In that case it will be 0. We don't need any borrowing, isn't that? So this plus 10 C1, okay, like 1 1, so it's fine. Here 2 2, it's again fine, isn't that? So 65, and similarly for here this one also we have 65, 10 C2 plus 10, 65, and then for y1 x1, okay, they can't be 0, so it has to be 9 C2. 9 C2 is 45, and then again, but see, are they distinct? I mean, that's also a case which we have to look for. They haven't said anything, so I think I can add up here again 10, not 10 exactly, 9, isn't that? Why? Because 0 0 is not a possibility. Okay, 1 1 2 2 is a possibility, isn't that? So that's it. But then there will be a problem. Wait. No, there won't be a problem, because we have ensured that y2 is greater than x2, y3 is greater than x3, and even if they are equal, there won't be a problem. So the answer should be in that case 54 into 65 whole square. Okay, okay, that's my way of looking at it. Though let me be very true to you people. When I solved it for the student here and I checked the answer, I didn't actually consider 10 cases here, equality cases. Okay, so the answer given was actually 45 into 55 whole square. So that's why you would have observed that I'm looking at the question, reading it again and again. But now when I'm solving it in front of you, I realize all of a sudden that there might be the case, because see, in the starting itself I started with the both are equal, so that might also be the case. So if anyone has any student has any doubt or any suggestion regarding it, let me know. Okay, any clarification required, let me know with the help of comment box. So I'm open to discuss it, because I myself solved it a day back. I got this as the answer which was given at the back side of the chapter also, but now when I'm solving, I'm getting this as the answer. Okay, so with the same person solving the same question 2 times and getting different answer. So right now I'm more convinced with this answer, though that was not the answer given at the end of the book. Okay, at the end of the chapter. So now moving to the next question. In how many ways can 14 identical toys be distributed among 3 boys so that each one get at least 1 toy, no 2 boys get equal number of toys? So 3 boys means we have 3 boxes, 14 identical objects. So at least everyone get at least 1. So see, since objects are identical, it's okay. So there's no, there's only one way in which you can put 1 object here, 1 object here, and 1 object here. Okay, because they are all identical. Let's say you have 10 red color balls, 14 red color balls, and you have to distribute 1 1 1 to each 3 kids. There's only one way, because all the objects are identical. Now, how many objects are we left with? Now we have to distribute 11 identical objects among 3 distinct boxes. How many ways? So again, I will go for that multinomial use. X1 here, I put X1 here, I put X2 here, I put X3 here. X1 plus X2 plus X3 is equal to 11. All possible ways of doing it, non-negative integral solution. So it's 12 C2, 11 plus 3 is 14. So I'm sorry, it's 13 C2, isn't that? So how much is it? 13 C2, 13 into 12 is 6, which is 78. Fine. But now, no boy get equal number of toys. Okay, now what are the possibility of distributing 11 objects? Okay, 11 objects among 3 persons having 2 persons. Not all 3 can get equal, because 11 is not divisible by 3. So 2 boys getting same number of objects. So 1 can be 0 0 11. Okay, another one can be like 1 1 9. 2 2 7, 3 3 5, and then 4, 4, 3, 5, 5, 1. That's it. Okay, that's it. So how many cases we got? We got here 1, 2, 3, 4, 5, 6 case. And then for every case we have 3 ways of distribution because objects are identical. Okay, so this can be distributed in 3 ways. 3 factorial by 2 factorial because 2 groups are identical. Here also 3 ways. So for every possible case we have only 3 ways for all the cases. So how many? 3 into 6 is equal to 18 ways. So subtract from there and you get 60 ways. So there are 60 ways of distributing 14 such identical toys in such a way among 3 students. So that's it. Now moving to the next question. F n upon is more than equal to 2, m is greater than n. Okay, right. M into n factorial is divisible by what? Okay, so see, I picked up this question just to discuss one very small thing. See, of course, m into n, when m and n both are greater than 2 is greater than. So m into n is greater than m plus n. And since m into n factorial, if n is like 7 is greater than 5. So when you write 7 factorial, you include 5 factorial, 7 into 6 into 5 factorial. So that means m into n factorial will definitely be divisible by any number which is less than m plus n, m into n. M into n factorial will be divisible by any number which is less than or equal to m into n for sure. So it's divisible by m plus n factorial also, no doubt about it. Similarly this, okay. Now see, why did I pick up this question? Just to discuss how to justify for general statement without taking example. So for that, how I did, that's what I want to discuss it with you people. I looked at it as distributing m into n distinct objects into n groups of identical size, into n groups of identical size. So every group will have m objects. So you will have m factorial into m factorial. How many times? N times. And then since identical size objects are there, identical size groups, so divide by n factorial. Now that's, we know that is an integer. So it could be integer only when this is divisible by this, yes or no? Because you have, it is an integer when you add into n factorial in denominator. Then also it's an integer. So of course this is divisible by this, and hence this is divisible by this. Reverse case. N groups, m objects, m groups, n objects. Okay, so that's it. So moving to the next question, 8th question here. 8 cross 8 square grid allows movement only along the left right. So the question is something like this. So this may need some patience here, bachcho. 3, 4, 5, 6, 7. One, two, three, four, five, 6. Okay. So that might be 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So the question is, you start from here, 0, 0, and you have to reach here, the point, let's say P, 8, 8. In how many ways? And the question is simple. See, I didn't go back because I spent a lot of time in solving this question. Okay. The first part is real easy. Is the total number of ways starting from the lower left corner to the upper right corner. So starting from lower left corner and going to the upper right corner, how many ways are there? That's a simple thing. Okay. So how many ways are there? Now how do I understand this is, see, let's say we have, let's say, you go along the horizontal line or along vertical line. You can't backtrack. Okay, so you can move from left to right or from down to up. That's it. Okay, so now you have 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. You have 9 horizontal line, and on those 9 horizontal line, you have to take 8 steps horizontally. 8 steps horizontally. So now, if I say I take x1 number of steps on the first line, x2 number of steps second line, x3 number of steps third line, x9 number of steps on the last line, and the total steps should be 8. Once you do it, you will be for sure here. How? Let's say you don't take any step. I mean x1 is 0. So on first line you didn't take any step. That means you moved up. Okay, then you went to the second line. Again second line someone says it's 0. Again that means you didn't take any step horizontally. That means you have to move up. You don't have a choice. Then someone says okay on x3, I mean third horizontal line, you take 2 steps. So you take 2 steps horizontally, you are here. And then you of course then you have to come to the fourth. So you have to move up. There's no choice. Now on the fourth line 1 step you move up, and this is how you can count. And the moment you complete 8 steps, so 2 plus 1 3, 4, 5, maybe no here, 6, 7, and then 8. You will reach 8, 8. That's it. So how many ways? Again, non-negative integral solution. So 16, 8 plus 9 is 17, 16 C8. That's your number of all possible ways of starting from here to here, such that you can move only from left to right or from up, down to upwards. Okay, that's it. Second part is interesting. It says B is the number of paths from lower corner to upper corner which do not intersect the diagonal joining the two corners. Okay, so if I draw the diagonal here, so it might not be the clear-cut diagonal. I mean, sorry, I'm really sorry, but okay, that's the diagonal. Okay, now if you draw the diagonal here, so it doesn't have to cut it. So see, as I said, I spend a lot of time in. So there's one very crude raw method which I actually use, on which I spend a lot of time, but somehow I could get the answer. So let me discuss it. It will take time. It took time, but since the way I thought, I just want to share it with you people. You like it or you don't like it is something else. Okay, so what I thought is, the point was, if I move along this on first, if I am talking about the vertical line, on first vertical line I can't take any step. Second vertical line I can't take any step more than 1. I mean this is 1. Third vertical line I can't take any step more than 2, because the moment you take more than 2 vertical steps you will cross the line, the diagonal. Similarly on fourth, not more than 3. So I said okay, x1 is less than equal to 0. So I am just forgetting it, because less than 0 won't contribute. Equal to 0, it has to be equal to 0 in that case. So I will say x1 for the second line, vertical line, less than equal to 1, x2 is less than equal to 2, x3 is less than equal to 3, and x8 is less than equal to 8. But is that sufficient? No, it's not sufficient either. Why? Because see, what it says is that on 7th maybe vertical line you can take any step which are less than equal to 7, but along with that, see, in that case if I select such that if I assign x3 as 2 and x7 as 6, so both the conditions are fulfilled. x3 is less than equal to 3 and x7 is less than equal to 7. But if I take 2 steps, I take 2 steps on third, I mean x3 is here, and then directly I go to this 7th one and I take 6 steps, 1, 2, 3, 4, 5, 6, we cross. You cross the line. What does that mean? That means till second vertical line, I'm missing the first one, the reference one, the y-axis. You can call it the y-axis. So I'm leaving it. So my count is starting from this one as the first one, from here onwards. Okay. So if I'm on the one line, first line, I can't take more than 1 step. Till second line, vertical line, I can't take more than 2 steps. Till third line, I can't take total more than 3 steps. Am I clear? I'm repeating, till second vertical line I can't take total more than 2 steps. Till 7th line I can't take total more than 7 steps. Okay, so hence if I say 2, 5, you won't cross. Or if I say x2 is 1, x3 is 1, x4 is 2, or x5 is 2, okay, and then x7. So if I take any number of steps which are less than equal to 7 in total, 1, 1, 4 and it is 3, then also you won't cross the diagonal. Okay, so to take care of this situation, what I thought was, so I just started with my multinomial again. So you might think that this is my favorite thing, but see, it all depends how you start thinking. Okay, so finally I zeroed down to this form. So on the first line, we have only two choices. Either you don't take any step or you take one step. On second line, you have three choices. No step, one step, two steps. Similarly, 1 plus x square plus x cube. Likewise for the fourth, x plus x square plus x cube plus x raised power 4. And then till the last one, 1 plus x square x raised power 8. Okay, now see, that actually I have to do mechanically. I have to do that mechanically. Okay, so that's why I said it took time, but then I was really happy because it could match with the answer. Okay, so that's why I'm sharing it with you. So I said, okay, since I can't take, so if I multiply these two, the power is representing the step. Okay, so what I don't have to consider is x cube. Why? Because till second line I can't take in totality more than 2 steps. So I multiplied 1 plus 2x plus 2x squared. That's it. I forgot the rest of the terms. Rest of the term is x cube is the only term left. Okay, then I multiplied it with this one. So again, this I can't go more than x cube. So when you multiply it with this one, so I collected the terms which are till x cube, because why? In totality you can't take more than 3 steps till third vertical line. So 1 plus, if you start multiplying, so it's x plus 2x is 3x, and then for x square it's x square, 2x square, 2x, 5x square. So like that I did, and then x cube, and then 2x cube, and then 5x cube. So then there's a pattern. Okay, so then you go ahead. So when you multiply, and again the same thing, I won't go beyond x raised power 4. So 1 plus 4x, and then you keep on adding them back. So 9, 5 plus 3 plus 1 is 9x square. Okay, then plus 5 is 14x cube, and last two have same coefficient, bachcho. Last two have same coefficient. So now if I multiply it with x raised power 5, so I'm writing it again here. If I have a space, no I don't have, just a minute, if I can add, just a minute. Okay, so if I just continue like that, yeah. So just if I try to continue it like that, so next one will be 1 plus 4, 4 plus 1 is 5, keep on adding, then add them, it's 14, x square, this is x, then add 14 to it, 28, x cube, then add 42, x raised power 4, and then 42, x raised power 5, till x raised power 5. Similarly, if you continue, so we have to reach x raised power 8. Okay, so I did it. Okay, so then next I am writing it directly. 1, add them, 6, add them, say 14 plus 5 plus 1 is 20, add them, 48, this is x cube, I am writing it under it, that's why, this is 90, x raised power 4, and then 132, x raised power 5, and then last will be 132, same, so 6, then add them, 1, 7, 27, 27 plus 48 is how much? 75, 90, 165, 132, if I am not wrong, 132, 297, and then again 132, so how much is it? 397, and then 400 something, how much is it? 429, last is also 429. So now 5, 6, and this is x raised power 7, and then you have to just so for x raised power 8 you have to just add them up. X raised power 8 you have to just add them up. So when you add them up, I got 1430. Okay, I got 1430 if I could remember it correctly. And then when I subtracted, okay, so that's actually that's unknown. I don't need to subtract. That's a way. That's all possible ways. So when you divide 16C8 by 1430, I think we will get answer. I remember. That's why I'm saying it, telling it here. It's 9. You people can check it, bachcho. Okay, you just try to check it. But along with that, see, there's one very good solution here, which I found later. I mean, which one I discovered while my discussion with one of my students. Okay, so he suggested, actually, he said, looking at the answer, okay, Actually, in the answer, it was given 16C8 minus 16C9 are those cases where you won't be crossing the diagonal. Okay, so the session was start with 1, 0, draw a diagonal which goes parallel to the original diagonal until here, which is 8, 7. Of course, it is parallel. Slope is 1 here, slope is 1 here. Okay, now he said that, he said means we, during discussion we spend a lot of time. So, let's say you start moving from here and then cross this diagonal, which we don't have to cross. Okay, and maybe then you reach here. You cross the diagonal 2 times. Now see, how can we look at this situation is, let me choose, which color shall I choose? I think this will be better. So from here till here, it's okay. The moment you cross this diagonal, the other diagonal, not the original diagonal, the other diagonal from 1, 0, 2, 8, 7, take the mirror image of the path. Take the mirror image of the path. So you take mirror image, so it will be here. Okay, rather it will be here. You come here. 1 more step, you come here. 3 steps, you take 3 steps. Okay, so this image will be in that case, wait. You have to come here. This one will be, wait. Okay, yeah, you cross here. So you are here and this image will be, did I counted more steps? 1, 2, 3, yeah. Wait, no. 1, its image is here, its image will be here, its image will be here. Okay, then its image will be 1 step up here, its image will be here, right, and of course this will meet here, and then see the portion of the path which you were above it. Okay, and then you reach it. Rather, I'm sorry, if you have to reach it, rather, sorry, wait, wait, which color? Yellow. So you reach here and then see, this image will be here. So this is 8, 7, this has to be 9, 7. Okay, so you end up, so when you take the mirror image of the path, when you cross this yellow diagonal, about this red diagonal, from the point where the path intersects the red diagonal, you end up reaching here actually. Okay, so how you end up reaching here? So that you can see, thoda sa upar niche, that you can see. Okay, what does that mean? What does that mean? That simply mean, okay, and now in that case you won't be crossing this diagonal. In that case you won't be crossing this diagonal, yellow diagonal. Okay, now what does that mean? That means now you have to walk from here till here. So the point was, if every time you cross the diagonal, the yellow diagonal, the diagonal of the 8 cross 8 grid, you will have an alternative path like this, and that will be a unique one for every such path. Okay, now here you have 9, 7, which add up to give 16. Okay, so now number of ways of reaching there. See, when they add up to 8 plus 8 is 16, you selected 8, 16C8. Here they add up to 9 plus 7 again 16, but here either you have to select 9 or you have to select 7. It's the same thing, 16C7 or 16C9. Okay, that means either you take 9 steps vertically or 7 steps vertically or 9 steps horizontally, you reach the same position. So 16C9. So that's what I said. Remove from 16C9 from 16C8, and that should be B. That should be B. Okay, now when you solve it, I think you will get 1430. That's what I did. So actually that was one method which I thought, but it's definitely very time taking and quite an exhaustive one. Okay, but then it's a method the way I thought. Okay, so you can of course say, what if this would have been 16 cross 16 grids? Of course that won't work, because that's that much calculation we can't do in that case. Okay, so that's it. So that was a good question according to me, so that's why we did it. 8 boxes are arranged in a row. In how many ways can 5 distinct balls be put into them such that each box contains at most one ball? No box can have more than one ball, and no 2 empty boxes are adjacent. So 8 boxes, 1, 2, 3, 4, 5, 6, 7, 8 in a row. So when you say that they are kept in a row, they are distinct because their position can make them distinct. Now there are how many? 5 distinct balls. So of course, and at most one ball in every box. So it's simple. 5 balls need only 5 boxes. Okay, so 3 boxes are to be empty. So you select 5. 1, 2, 3. 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6, 7, 8. So no 2 empty boxes are adjacent. Okay, right. In that case, I will go the other way around. I will say, okay, let's select the empty box. So that was fine. Okay, no 2 boxes are empty boxes are adjacent. 1, 2, maybe 3. So again, I will use the same method. You will say, okay, again and again you are using the same method, because once I see it, I really get comfortable in it. You have 4 possibilities. So of course, they add up to give 5. Because when you keep 3 boxes empty aside, you are left with 5. So 5, such that x2 and x3 are 1. They are not 1, they shouldn't be 0, they can't be 0, whereas x1 and x4 can be 0. So y1 plus y2 plus y3 plus y4 is to be 3, because x2 is 1 plus y2, x3 is 1 plus y3, we have already used it. So number of non-negative integral solution is how much? 6c3. Isn't that? How much is it? 6c3 is 3 factorial is 20. It's 20. Okay, now 5 boxes and 5 balls, distinct in how many ways? Into 5 factorial. How much is it? So 120 into 20 is, I think, 2400. Right? Yeah, that's it. Now the other possibility is 4 boxes, but then 4 boxes empty means you need to put at least 2 balls in one box, which is not a possibility. So that should be the answer. So that's it. Now moving to the next question. The 10th one, number of ways 3 girls and 5 boys can be seated around a circular table such that no 2 girls sit together and not more than 2 boys sit between 2 girls. So no 2 girls sit together. Okay, so for that case again, I will make sit boys first, because that's the normal procedure I follow when no 2 particular type of object has to appear together. Okay, so in how many ways you can make sit 5 boys along a circular table? In 4 factorial ways. Okay, now you have to select 3 gaps for 3 girls, but 2 boys, not more than 2 boys should be between any 2 girls. Okay, so that's it. So that means, see, we have 1, 2, 3, 4, 5. So total ways of selecting is 5c3, but from those ways we have to remove those number of ways where you have more than 2 boys between any 2 girls, and the possibility is only 3 boys. Like if I select 1, 2, 3 consecutive, these 3 spaces, then these 3 boys get together without any girl between them. So that's it. So you don't have to count, you don't have to select just 3 consecutive spaces. In how many ways? In 5 ways. 1, start from, then 2, 3, 4, 5. You start from here, you end up here. So 5 ways, and that's it, and then you make it this. So see, that's the actual form of the answer, so that's why I am solving it in this form. So that's exactly the form of the answer is. Okay, so now moving, so that was a simple one, of course. In a plane, there are 2 families of lines, y is equal to x plus r. See, distance between, so y is equal to x, y is equal to x plus 1, y is equal to x plus 2, x plus 3, x plus 4. Okay, now distance between any 2 lines is 1 by root 2, if I am not wrong, yeah. Consecutive line. Okay, now the number of diagonals length is 2 units. So if you select a square and the lines are perpendicular, I mean this family of line and this family of line, they are perpendicular lines. So in any case, you are going to get a rectangle. Right, select any two member from this and any two member from a pair of lines which are perpendicular. So you'll definitely get a rectangle. To ensure that it's a square, the distance between the two selected lines, which are, let's say, this one y is equal to x plus r, should be same as the distance between two selected lines from the family y is equal to minus x plus r, to ensure it's a square. Okay, but first I am seeing when will we get the diagonal length as 2. For that it should be root 2 and root 2. That means, what does that mean? We need to select with a gap of 2. That's it. That's it, isn't that? So how many ways? 1, 2 and 3. Just 3 ways. So 3 ways of selecting any two line from here and 3 ways of selecting any two line from there. So it's 9 ways, as simple as that. Okay, so that's see, this method might be important if the number would have been larger. Okay, so then this will help you. Okay, then next is first 9 natural numbers are to be divided in 3 boxes: group 1, group 2, group 3. Okay, containing each in how many different ways you can. So sum of numbers in each group is odd. So when can you have sum of 3 numbers as odd? The only possibility is when all the 3 numbers are odd, or 2 are even and 1 is odd. So we have 9 natural numbers. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So out of these 9, 5 are odd and 4 are even. So I will distribute first even. So in how many ways? 2, 2, 0. So number of ways of grouping is 4 factorial by 2 factorial into 2 factorial into 2 factorial, because 2 are of identical size. There's no value of 0 here. Okay, no sense of 0. Okay, so that's it. So in how many ways you can put? So 2 factorial is 24. So it's 3 ways of doing it. Fine. In how many ways you can put them in the boxes? So I think in 3 factorial ways, isn't that? Because this has 2 choice and 2 choice into 3 factorial. So how many? So that's 18. 18 ways of putting 2 even numbers, two even number in 2 boxes. That's it. Now, for every, see, now we have one box which is empty. For that you have to select 5 out of 3. 5 out of 3. Okay, so any 3 can go to that box and that's it. But, and for remaining one, so you are left with 2. So 1 here, 1 there, so it should be into 2. So let's count. So 18 into 5C3 is 5C2 into 10 into 2. So is that an option? 360, that's an option. That should be the answer. Okay, so that's it. So now moving to the second last question here. There are 15, I think. There are 5 balls of different colors and 5 boxes of colors same as that of the ball. So that means red ball, red box, green box, yellow box, orange ball, orange box, white ball, white box. The number of ways in which balls could be placed such that exactly 2 balls goes to the box. Let's say I selected 2 out of 5, 5C2 ways. Red ball, green ball. I put them in their own boxes. Now we are left with 3 balls, yellow, orange, white, and 3 corresponding boxes. Now exactly 2 balls goes to their box. So that means 3 are de-arranged. 3 balls are de-arranged. No other ball out of those 3 will go to its own box. How many ways? So it's into D3. Now what's the formula for number of ways of de-arrangement for n distinct objects? Is n factorial into 1 by 0 factorial minus 1 by 1 factorial plus 1 by 2 factorial minus 1 by 3 factorial, and so on till you reach 1 by n factorial, positive or negative sign. That will be decided on the basis of whether n is even or odd. Okay, so 5C2 is 10 and then D3, so it's 3 factorial. And see, this is of no use, actually they get cancelled. So 3 minus 1 is 2. Rather, 3 factorial will be gone. Oh, it's 20. It's 20. That's it. So that's it. So that was a question on de-arrangement. So that's why I just picked it up. Next is, an octopus has 1 sock and 1 shoe for each of its 8 legs. So there are 16 objects. There are 16 objects. Now many different order can the octopus put on the socks and shoes, assuming that each leg and the sock must be put on the before the shoe. Of course, you have to wear socks before the shoes. Okay. Now see, there are 16 objects. I am assuming them to be all distinct. There are 16 distinct objects, 8 socks and 8 shoes. In how many ways octopus can put them in 8 legs such that socks should appear before shoes? How do I look at this question, the situation? is like there are 18 person in a class, 8 girls, 8 boys, such that, okay, now how can you how can you group them, right? 18 boys with 8 boys with 8 different color t-shirt, and 8 girls with 8 same color t-shirt which the boy like. For 8 boys you select 8 colors, and then same 8 colors for 8 girls. Now such that boy and girl with same t-shirt always get arranged so that a girl is always before the boy in the queue. Okay, now how will you do it? You will say, okay, 16 factorial are the total ways of arrangement. For a girl and a boy with white color t-shirt, there is no choice of arrangement. Why? Because always the white color t-shirt girl has to stand before the white color t-shirt boy. So when you don't have a choice of arrangement, what do? See, in permutation combination, the easiest way is you consider them to be identical. We consider them to be identical because see, if there is no choice of arrangement, that means a white color t-shirt boy and girl, they can be arranged in only one way, because a girl has to always stand before the boy. There is only one way. And in permutation combination, if you have only one way of arrangement, you can easily assume those objects to be identical. So it's 2 factorial. Similarly for yellow color t-shirt boy and girl, 2 factorial, 2 how many times? So it's like 2 factorial is for 8. That's it. That's it. So this is how I took an analogy to solve this question. So I took an analogy from there and got this answer. So that's it. So those were the questions of PNC for you people. In the next video, we'll be coming up with another chapter of algebra, most likely the complex number बच्चों.